Once a year. Okay, thank you for the invitation and thank you for coming. So I'm going to talk about I wrote some recent results on geometric transversals. I might only show you one recent result, and then some open questions that we have. This is joint work with Otfried, Cheong, and Xavier, Goaoc, and this is so some ongoing work that's going to be put together to something. This is one part of some ongoing work, I would say. And geometric transversals, probably few of you know what this is. So that much of what I will say is, what happened now? Did I touch this? But this, no, laptop was fine. Okay, so like I said, most of you won't know what geometric transversals mean. This is something that now I didn't do it. For sure. Oh, there it's okay. But it's something that us three used to work on quite a bit for a while back, 10 years ago or more. In fact, it's how I met both of them, was working on these kind of problems. And then, well, we did some other things. And it was very fun to return back to this kind of problems. So much of what I'm going to first tell you about what geometric transversals are and put some context into these things. Okay, so here's the basic definition. I want to see it from here. You can see. Okay, so throughout F is going to be a finite family of convex sets in the d-dimensional space. All right, I'll try to reserve that letter F for this. And a K transversal to F is just another word for an affine flat of dimension K that intersects every member of the family. Okay? So K will be some integer between 0 and, I guess you could put D, but that's not very interesting. So generally between 0 and D minus 1. Okay? And so I drew some examples here. Here are 4 convex sets, and there's a point there. That's a 0-dimensional flat. And that is a point transversal. Okay, so those 4 sets have a point transversal. And on the right figure, there are another 4 convex sets, and there's no point transversal, but there are some line transversals, right? There's a line here that intersects all of them. There's a line here that intersects all of them. And basically, what we want to understand are what are conditions that guarantee that you can find such a transversal, maybe combinatorial conditions. We want to understand what is the structure of these transversals and various things like this. Maybe the family doesn't have a transversal, but there are subfamilies of transversals. We want to understand the combinatorics of these families. And it is combinatorial. We always consider F to be a finite family, and we want to understand the subfamilies, how they interact and how they have transversals. And one of the first subtle things that you might notice here, so there I'm illustrating a 0 transversal. And then you can, for example, ask, what is the set or space of all 0 transversals? It's just this intersection. It's a convex set. Now, here you see I drew 2 different line transversals. And you notice something maybe. The space of line transversals is not connected. I cannot go from this transversal to this transversal while staying transversal to all the sets of the whole time. So that already illustrates that there is some subtle difference between point transversals and line transversals, for example. Right? And yeah, typically we would say point transversals, line transversals, or hyperplane transversals. And that's just in case I use those words instead, what they mean. So that's 0, K is 0, K is 1, K is D minus 1. Okay, so some context about these transversals. The most studied case is when k is 0, so point transversal. This is the by far most studied and well understood case. And it kind of starts here with Helly's theorem in RD, which says that this family F has a 0 transversal if and only if every subfamily of size at most d plus 1 has a 0 transversal. So we have necessary and sufficient conditions for a family to have a 0 transversal. And this gives rise to a whole industry of results and research. Okay, so often it's called to study the intersection patterns of convex sets. And in some sense, it deals with the combinatorial structure and properties of what are called D-representable hypergraphs. So given a family of convex sets in RD, I will make a hypergraph as follows. I take for every member of the family, every set in the family, I'll make a vertex. So represent them by vertices. And if d plus 1 of them have a non-empty intersection, I'll put a hyperedge there. So it's a d plus 1 uniform hypergraph. And in order for me to understand the total structure of the family of all subfamilies of size at least d plus 1 that have non-empty intersection, it's enough for me to understand this hypergraph. So a subfamily that intersects is the same as a clique in that D-representable hypergraph, right? And so basically the intersection patterns of convex sets is really studying the sort of combinatorial structures and properties of these hypergraphs. And that is not a trivial task in itself. Already D equals, and there are a lot of directions going from this. So already in D equals 1, what are these one representable hypergraphs? They're precisely what they call interval graphs. I guess were characterized in the 50s or something like this, right? And once you start thinking about those, you can go further and you see interval graphs are a special case of chordal graphs, and a lot of the properties of interval graphs actually hold here. And then chordal graphs are perfect graphs, and maybe you go into chi-band. A lot of directions that you could imagine just going from the case D equals 1, right? And if D is greater than 1, then these hypergraphs would be called D-representable. And you generalize this to something called D-collapsible. And then that's some combinatorial condition, which tells you somehow how you can construct these hypergraphs inductively by adding more and more vertices. You might go further, and more general than this are some algebraic properties called D-Larray, or some dual version, they're called Coe and Macaulay. And you might have heard of these, studying algebraic combinatorics. So my purpose of this slide is just to show you that even just studying 0 transversals leads to a lot of directions of research. And so there's more than enough for more than what a single person can understand if you want to understand all of these things. I want to focus on one specific property that was discovered for these 0 transversals, and that's the next theorem. It's called the Weakepsilon net theorem. And this is one of the most intriguing theorems or properties of convex sets. It's due to Allon, Barani, Ferretti, and Kleitman. And it says the following. So you have a family, F, as usual, is this family of convex sets. But there's an additional condition here. Suppose there's a finite set of points, S, such that for every convex set in your family, this set intersects. So the top here is counting how many points the set C intersects. Divided by S, this should be greater than some fixed epsilon. And if this is true, so if there exists such a set S, then it means that you can partition your family into a constant number of parts, M, where M depends only on that epsilon and the dimension D, such that each of these Fi's has a 0 transversal. So if you think of the hypergraph formulation I gave you earlier, you're partitioning that hypergraph into cliques. And it's saying that you can partition into a bounded number of cliques, depending only on the dimension you're in and that epsilon. Right? And so another way of thinking of this is you're given your family of convex sets, and this additional condition, you can think of it as defining a probability measure. Right? So this S is defining a probability measure on the space. And for any convex set in your family, if you were to pick a point randomly from that measure with probability greater than epsilon, you will hit that convex set. Right? That's what this is saying. And so if you can define such a measure, then it means you can partition this family into a bounded number of intersecting subfamilies. Right? Or in other words, you can partition that hypergraph into m cliques. So you have your family of convex sets in the space, and you're saying, suppose there is a probability measure, a finite one here. Right? So S is defined by a finite set. And whenever you take a convex set, if you pick uniformly at random from that set S, from your measure, the probability that you hit the convex set is at least epsilon, or greater than epsilon. Is that clear? Yeah. So by the way, stop me anytime to ask these kind of questions, because everything should be pretty elementary what I say. So there's no reason for you not to understand everything. If you don't understand something, it's because I didn't do a good enough job explaining it. Right? So this is a kind of rather deep property. It has a lot of applications. And there is a combinatorial analog, which you may know, called the epsilon net theorem for hypergraphs. And it's for hypergraphs with bounded VC dimension. And here, this is for convex sets and points. And what's important to note is that, so basically what it tells me is that once this measure exists, I can pick m points that will together pierce all the sets of my family. Those points that you find here, that pierce these guys, will typically not be points from S. Typically, you cannot use the points from S. And why they call it a weak epsilon theorem, because the piercing points are not selected from the input measure. Okay, so that is the weak epsilon theorem. And one of the main problems, some people even say it's one of the most important problems in discrete geometry, is to determine the growth rate of this function. And the known bounds are here. They're not very good. So here's the lower bound from 10 years ago by Book, Matuszek, and Nivash, which shows that it's superlinear when d is greater than 1. And their proof is very interesting and introduces a technique or construction called what they call the stretch grid, or staircase convexity. It's a very nice tool that has many other applications also. That's how they can construct this lower bound. The upper bound is a very recent breakthrough due to Nathan Rubin. And you see it's really far apart. And actually Rubin's proof, which I have not verified at all, is a more than 100-page paper. And what he really does, very technical paper, and what he does is it used to be without that half there. And his huge breakthrough is to get this plus half here. So that's sort of the status of understanding that function. So that's considered a very big open problem. Oh, gamma is some arbitrarily small constant. Sorry. Yeah. So arbitrarily close to this half minus d. And the weak epsilon theorem, it was invented by these guys in order to prove something called the Hadwiger-de Brunner PQ conjecture, which was a famous open problem also from the 1950s, I think, by Hadwiger and de Brunner. And their problem says, their conjecture was that suppose you have a family of convex sets, and whenever you take, and it has the property that whenever you take p of them, some q of them will intersect. Then it is possible to find a finite set of points that intersects the whole family. Now p should be greater or equal to q, and q should be greater or equal to d plus 1. And basically how Alon and Kleitman prove this is, suppose you have a family that has the pq property. Among any p, there's some q that intersect. So in the hypergraph, this kind of means that whenever you look at p vertices in the hypergraph, there's a clique of size q. So the cliques are kind of regularly distributed throughout. So the way that they prove this is, okay, suppose you have this property, then they show that depending only on P and Q, they can compute an epsilon, and then they can define such a measure in the space, this set S, so that your family satisfies this property for that given epsilon that depends only on P, Q, and D, and then the proof is done. Right? Of course, it's some technicality how to define this measure, but that's the basic idea of their proof. Yeah. And yeah, recent work, well, this is not so recent, but a paper by Alon, Kalai, and them, Moran and Yehudayev, and then myself and Dongyevi. If you combine all our results, we could prove something that this is equivalent to something called bounded Rado number in a very abstract setting. I think that was what last time I was here a year ago, I mentioned about that. So anyway, that's sort of the weak epsilon theorem, and it's still one of the most important results about intersection patterns of convex sets. And we will come back to this later on. So now let me increase the K. Remember, we're talking about K transversals. This is for zero transversals. Now let me increase K and start making some observations. The first observation is that there is no Helly theorem anymore when K is greater than 0. And it's very easy to see. The colors aren't really showing very clearly here. But let me prove to you there's no Helly theorem. For this is the case of line transversals in the plane. So take here a regular n-gon, right? And the line up here and the line out here below, they are determining the width of the polygon. Okay, so that's the narrowest strip that contains the polygon. It will be parallel to one of the edges, and when it's an odd polygon, it will be touching a vertex here. And what the figure is illustrating is that when you drop one vertex, you will reduce the width. Right? And that is kind of obvious. Now, take this smaller width here, and at each vertex, you blow up that vertex to become a disk centered at that vertex, whose radius is half this smaller width. Right? Then, those disks will precisely be intersected by the line which is the central line of that strip. Right? And that's the picture here. So if I drop one disk, I can intersect the remaining guys by a single line. But if I put that disk back, I cannot intersect all of them. Okay? And so this works for any n. So there is no Helly theorem. There's no number that says that if every 102 of them have a line transversal, then they all have a line transversal. Simply does not work. So making this one transversal hypergraph, you could do it, but it does not look as nice as the case for zero transversals. That's the basics. That's the basic point of this, right? That you don't have such a nice theory, or it indicates that maybe there's not going to be as nice a theory. I should mention that the situation is different if you impose further geometric constraints. So, for example, this picture is unit disks. Now, if you additionally assume that the unit disks were pairwise disjoint, meaning they're kind of far apart, then there would be a Helly theorem. And there are all kinds of different geometric constraints you could add here to get a Helly theory. And among the things that me and Xavier and Otfried studied many years ago was stuff like this. But that is really more geometrical, and I don't want to get into that. But there is a way to go further there. But we would like to understand this unconstrained situation. And in general, it's very difficult. Or very difficult, meaning that most of the things we try, they simply don't work. They're false. So maybe it's difficult to come up with the right question, is maybe the main problem here. Okay, but some things are known. I won't mention all of them, but I'll mention this result by Alon and Kalai, which is a weak epsilon theorem for hyperplane transversals. Okay? And you see, it's the same statement as before, except that, so I have a finite family of convex sets, and now suppose there's a finite set of hyperplanes, such that, and here is, on the top, I'm counting, for a given set C, I'm counting how many hyperplanes intersects that set C, and dividing by the number of hyperplanes. right? Then I can partition my family into n parts, depending only on epsilon and d, such that each part has a hyperplane transversal. Okay, so it's the same question, except that the measure you're defining now is sort of in the space of hyperplanes, right? And it turns out that you do get a weak epsilon net theorem. So even though you don't have a Helly theorem, you still get this weak epsilon net theorem. So that is very positive. And Alon and Kalai use this to prove a generalization of this PQ theorem to hyperplane transversals. So that is known. The proof of the weak epsilon net for hyperplane transversals is, as far as I know, it's quite different from the proof for the point transversal version of weak epsilon net theorem. Okay. And recently, it was conjectured by Barney and Kalai that this weak epsilon net type theorem should generalize to K transversals. Specifically, in their survey, they formulated for line transversals. Right? So, and in fact, line transversals in R3 is what they conjecture specifically. So their conjecture would be, let F be a finite family of convex sets in R3. Suppose there's a finite set of lines such that every set of your family intersects a positive fraction of the lines. Then you should be able to partition your family into a fixed number of parts, each one intersected by a line. Right? Okay. And then here is the bad news. That is not true. And so this is basically the recent result I will show you today. And it's not too difficult. It's a little bit tricky. But I think I can show you the whole construction. Okay, so the theorem is, in fact, in any dimension. So for every dimension greater or equal to 3, every epsilon between 0 and 1, and any integer t, I'll give you a finite family of convex sets. I'll give you a finite set of lines that are in general position, such that every set intersects a positive and epsilon fraction of the lines, and any set of t lines misses at least one set of your family. Okay? Is it clear? There might be one question: what does general position mean? So general position means, so I have a family of lines, right? And they are points of a manifold called a Grassmannian manifold. Okay? So you can parameterize the space of lines. And in general position means basically that I can perturb within an open neighborhood of each of these lines, I can choose a nearby line in this neighborhood. So for every line, geometrically it's much simpler. Here's one of the lines in my construction. I can take a point and a little disk around here, and a little disk 2 points on the line, and I can replace every line by, so this line can be replaced by choosing an arbitrary point in that neighborhood and an arbitrary point in that neighborhood, and replaced by the line spanned by those 2 points. So I could do that for all the lines in my construction, and the property should still hold. Right? Yeah, the theorem will still hold for that new set of lines. Okay, so it's stable in a sense. Because you could maybe imagine that there's some very specific, rigid family of lines for which this fails, but as soon as you start perturbing things a little bit, it doesn't work anymore. Imaginable.
The no three line intersected in a single point, no two line are on the same plane.
Okay, so no two lines should intersect, yes. That would, no two lines should intersect. That's so yeah, no two lines should intersect. No three.
No two will be parallel to.
No two should be parallel. So no two are contained in a common plane. No three are parallel to a common plane. Maybe no 5 should be intersected by a line. But it starts getting a little more tricky to define this. But so it's easier to think of this topologically, that you're in a space. So you have your Grassmannian, you take if we're looking at the set of n lines, you look at the n-fold product of this, and you're taking an open neighborhood there, and you're allowed to perturb within that open neighborhood. I think that's the best way to think about it. But, well, of course.
Transversal, if you have this end on
Yeah.
showing there's no Halley theorem, but we have a DQ theorem. This does not disprove that possibility.
For lines in R3. There is no PQ theorem either for lines in R3. That's simpler than this, actually. Yeah. I don't know if specifically this implies that, but probably you could take our construction and make a counterexample to the PQ theorem also. Yeah. So basically, what this example shows, which we have many other examples earlier, is that as soon as you're looking at lines in R3 or above, things start failing. And we don't know what is the right question. People like me really want a theory for line transversals in R3. And we just don't have the right questions at the moment. So that's why it was exciting when Barney and Kalai made this conjecture. Wow, maybe that is the right question. Nobody thought of that before. But unfortunately, the sad truth is that it doesn't work. Yeah. One thing we don't know, our construction is really only for lines. We don't know how to do this, for example, for two planes in RD. So D should be greater than 4, or else a two-plane is a hyperplane, right? But for example, two planes in R4, we don't know. I mean, I would be very surprised if there was a weak epsilon theorem in this case. But we don't know how to disprove it. This is something very specific for lines that we can do. And yeah, so I want to show you the construction. And even I think I can show in full detail. It's not too difficult, but it's there's some subtleties along the way. So let me just see that I have enough colors. Blue. Okay. So the construction is based on the following nice surface called the hyperbolic paraboloid. And this is a picture I found on the Smithsonian Institute's homepage, where they have some physical models of this surface. All right, so this is a ruled surface, doubly ruled surface, which means that for every point in this surface, there is contained inside two lines that are in the surface. And there's a continuous family of lines going this way. That's one ruling. And there's another family of lines living in the surface going this way. That's the second ruling. Right? And this is the sort of basis of our construction, is this surface. And for convenience, we use a parametrization of that surface, which is this one. So x, y, z is R3. It's very simple. So there is another surface called the hyperboloid, which we could have used for our construction also, but this is such much easier equation to work with, so prefer this. Right? And here you see the rulings. If you keep x fixed, right, you see, and you increase y, sorry. Yeah, for every, you keep x fixed, you get a line, right? Y, so those are the two rulings. So the picture kind of looks like this. So I'll look at this from above. I have the x-axis and y-axis, and I have lines like this, but they're coming out. The z-axis is going towards you. You have lines this way, and they're coming out. Right? Here, they're going in. Right? So that's this surface viewed from above. Okay, so there's a technical lemma, and it's the following. So this is the key lemma. Okay, so take any set, finite set of lines, B, so blue lines, from one of the rulings. Okay? On the hyperboloid. Paraboloid. And then take any other set R of red lines in R3, such that those are disjoint. No blue line is equal to red line. Then I can find a compact convex set that intersects every line in B, but misses every line in R. Okay? So I have these blue lines, these guys here, and you are allowed to choose 2,000 red lines. But you cannot choose them same as any of the blue lines. And no matter how you choose them, I will show you there's a convex set that hits the blue lines but misses the red lines. Is it clear? Not clear that it's true, but is the statement clear? Okay, so here is an example. Here are the blue lines from the one ruling. And you choose some red lines. Now you can choose some red lines from the other ruling. You can choose some red lines from the same ruling. And then you can choose some red lines that kind of cut through the surface that are not in any ruling. And I'll cut in at most 2 points of this surface. Right? And in this picture, I will find some convex set that does not hit any of the red lines, but hits every blue line. Okay? And here, I'll show you why this is true. So suppose here are my blue lines. Like that, right? And your red lines, there are some of these. There might be some of these. See, red lines. And then there are these other lines that kind of cut through the surface, so maybe they intersect in some points living around. Finite number of them, like this, right? Okay, so now I'm going to look at this picture, and I'm going to choose some line that's kind of far away from all of these points and all of these lines here. And it's going to be in this second ruling. So this line like this, right? Now clearly, okay, so what I'm going to draw here is sort of, so think of this yellow thing as a plane like this. And let's look at the cross section, right? So the cross section here is a line. It's a line of the ruling. And you'll see these blue lines like this, and these red lines. These red lines are going to be nowhere near that cross section. And these lines that are kind of cutting through might, like this. Yeah? Now, if I take the convex hull of the blue points, that is such a compact convex set, but it's no good because there will be these red lines that intersect it. Right? But now, just take this line and twist it a little bit. Okay, so this line had equation x equals a, this plane. This plane has equation x minus a, y equals some big N times x minus a. That's this line here, right? And what does the cross section there look like? Well, if you plug this in here, you get a parabola, right? For y. So it's a parabola like this. And you have the blue points. You have the red points. But this is a convex curve. So when I take the convex hull, I'm going to miss those red points, right? But there were these red points. They could be here, right? So those red points possibly could intersect that convex polygon there. But now you take the limit. You let n go to infinity. This polygon converges to that segment. So at some point, it's going to be far away from those red points there. And there's your convex set. Okay? So that's how you find your convex set. Okay, so then it's not too hard to construct our counterexample. So I included a theorem up there as a reminder. Okay, so t was given and epsilon is given, right? And then I pick some integer n, which is bigger than t over 1 minus epsilon. And then I take a set of n lines in one of the rulings. So those are those blue lines. Take n of those. And then you look at f hat is the family of all polytopes spanned by more than epsilon n of the lines. Okay, so you take epsilon n of these lines, and a polytope spanned by that means you choose 1 point on each of them and take the convex hull. Okay? So you look at all of those polytopes. What did this previous lemma say? That if I want to pierce So given one subfamily of epsilon n lines, and look at all the polytopes. If I want to pierce those with some red line, how can I pierce them? If I have a finite set of red lines and I want to pierce those, how should I pierce those? I need to choose one of the blue lines. Right? It's the only way. That's what the previous lemma said. The only way to pierce those is by actually choosing one of the lines, one of the epsilon n lines. So if you consider now T is a finite set of lines that pierces all the members of F hat, well then, for any subset which has size greater than epsilon n, that piercing set must contain one of those lines. Right? And this, then you just calculate. It means that you need size of T must be at least this. Okay? Very simple. So who sees why this is not a counterexample? So the theorem is there. And this is not a counterexample. Or this is not, does not prove the theorem. It's just almost a counterexample. Yes. F hat is not finite. It's an infinite family of convex sets. And another thing. No, not at all. Right? So the lines are not in general position, and it's not a finite family of convex sets. So you need to fix that. But you can do that by some subtle tricks. Standard tricks, but you need to sort of do it in the right order. So first you reduce to finite. And so you make a hypergraph whose vertex set is this infinite family. And the edge set are the subfamilies that are minimal and have no line transversal. So it's the subfamilies that have no line transversal, counterexamples to Helly theorem, but every subfamily of those, proper subfamily, has a line transversal. So that's an infinite hypergraph. And then, since the members of F are compact, it means that the edges of that hypergraph are finite. And this is from the finite intersection property of compact sets. I can go through this. I won't go through the details of that, but you can maybe understand. Okay, what does it mean that no T lines intersect every member of, or all the members of F hat? It means that that hypergraph, that infinite hypergraph, has chromatic number greater than T. Okay? So whenever you partition into T, the vertex set into T parts, one of those parts does not have a line transversal, which means there's an edge inside there. So the chromatic number is greater than T. So by the compactness principle, there's a finite induced subhypergraph with chromatic number greater than T. So therefore, I cut down my infinite family to finite. And then, oops. This is a little unstable, this. Maybe I'll plug this one too. Yep. Back.
Yeah, one back. So is it also from compact, so that we have edges at all? Is that a consequence of compactness as well, or non-empty edges or something?
Non-empty. That there are edges. Yeah. That's because I can't pierce. I mean, I cannot pierce everybody by a line.
Right. But so a minimal family may not exist, right? So there may not be. So since we are talking infinite here, at least.
Oh, okay. Think I see what you mean. But no. But if every finite subfamily has a line transversal, then the whole family has a line transversal. This is also compactness.
That was basically my.
Okay. So that answers your question, right? Yeah, good. Yeah. So you do need to use the compactness of these members and so on. And then once you have it finite, then it's not too hard to perturb things into general position. So now I have my lines. They're still not in general position, but I have a finite family that does the job. Finite family of convex sets. And then you look at T tuples of lines, and you know that none of those T tuples intersects every member. And the T tuple. Oh, so there's a big ball that contains all your whole family F. Now your finite family F. Right? And the T tuples of lines that intersect that big ball B is a compact set. And by compactness, again, it means that you can find some absolute delta such that every T tuple of lines is at least distance delta from some member. And then you can blow up each member by a small delta half. Then it means that all your lines, your original lines not in general position, so L hat, intersects each ball in interior points, and now you can perturb them a little bit. Okay, so that is sort of the order in which we have to do things. So we did not find any way, so that sort of is the end of the proof. So what we tried first, which we failed, was we had our construction on the hyperboloid. Now, okay, we want it in general position. Move these so that they're not in the hyperboloid, but then we couldn't verify that we have our right property. So sort of it was very subtle. You have to do it in this direction. That you're on the hyperboloid, you have this infinite family of convex sets. First, you cut that down to finite. Then you can do it in this way. And we have no way to do it in another way. So, yeah. So anyway, that is the counterexample, and disappointing because people were hoping that this might be the one thing that makes a theory for line transversals work in R3, but it doesn't. Okay, so that was that construction. Now there are some other questions. So here's a related question, and this is a question we don't understand at all. Don't really know if it's interesting, but it's interesting because we can't really say anything about it. Okay, so now it's related to the hyperboloid construction or paraboloid. So take a set of B blue lines and R red lines in R3 in general position. Okay, and suppose that the blue and red lines are distinct. They're all generic lines in general position. Is there a convex set that intersects the blue lines and is disjoint from all the red lines? So our construction was kind of a counterexample to this. Or, yeah, our construction was family of blue lines, and no matter what red lines you put in, there's a convex set that intersects the blue, but it's disjoint from the red. But like I said, those lines were not in general position. And so our question is, can you, if they're in general position, what is the answer here? So if B is at most 3 or R is at most 2, the answer is yes. I can always find that convex set. And then maybe surprisingly, we found a configuration with 9 blue lines, 13 red lines, such that no matter what convex set you take that intersects the blue lines will be intersected by one of the red lines. Such a configuration exists. And it's in general position. I'll give it to you. You can go in and you can sort of think, knock each line a little bit. It'll still work. So this is really in general position. And one question is, what is the typical answer? Suppose you take a random set of lines that intersect the unit ball. Half of them are red, half of them are blue. Is it usually yes or usually no, or I have no idea. I have no idea what the answer could be. You can think of it as a game. Blue player plays his blue lines, red player plays his, then red player comes and tries to shoot all the convex sets spanned by the blue line, right? Is it true that if B, you start with some B greater than 3, if red player now has sufficiently many lines, so say B is 10, red player has 2 million lines, can they always win the game and kill all them? I don't know. But really, this depends on things being in general position. Or else you take the hyperboloid. construction that we have. So there is some question here, or many questions here. I don't know which one is interesting, but basically we don't understand this at all. And it also illustrates the difference between points transversals and line transversals. Imagine this game where you're playing with point transversals instead. Blue player takes a bunch of blue points, and now red player is supposed to use his red points to intersect every convex set that contains the blue points. The game is trivial. You just put a red point in the convex hull of the blue points. You're done, right? But as soon as it's lines in R3, it's not clear what is going on here. So we do wonder about this. And this configuration is not too complicated, but maybe I'll show it now. Okay, so last slide, some further questions. And this is where we maybe think that the whole theory could be saved. And that is, basically, we don't look at families of convex sets, we look at families of pairwise intersecting convex sets. Okay, so we add a condition that every pair has a point transversal. Then maybe some theory of line transversals will arise. And first question, suppose you have a sufficiently large finite family of pairwise intersecting convex sets in R3. Does there exist a line that intersects 100 of them? Okay, so if you make the family sufficiently large, can you always find a line that intersects 100 of the sets? We don't know. In fact, a conjecture by Nathan Rubin and Edgardo Roldan and Leonardo Martinez, they conjecture something stronger, that there's some linear relation here. That you can always, for a finite family, you can always intersect a positive fraction of them by a line. But even this question is not, we don't know how to answer. Second question, let F be a family of n pairwise intersecting convex sets in R3. How many connected components can the space of line transversals have? I showed you in the beginning an example of 4 convex sets, and they had 2 connected components, the space of line transversals. But in R3, it's very different. If you have 3 convex sets, if you have 3 pairwise disjoint convex sets, the space of line transversals can have most 3 connected components. If you have 4 pairwise disjoint convex sets in R3, you can have arbitrarily many connected components. So, and this sort of explains one of the reasons why there's not a good theory. But what if the sets are pairwise intersecting? Maybe then the number of connected components can be controlled as some function of n. I don't know. And so then the last question, is there a weak epsilon theorem for families of pairwise intersecting convex sets? So, okay, it was the last slide. Pairwise intersecting convex sets. And I don't see how, oh, it came back. I don't see how our construction works with pairwise intersecting convex sets. So there, I think that could be the right question to ask. And that's what maybe people believe, is that this pairwise intersecting, this is where it is. And it makes sense, maybe, that in order to control the K transversals, or to have some theory about K transversals, you need to make assumptions about the K minus 1 transversals. And that's sort of the hope in this whole game. Okay, so that is the end. And I found this nice picture of a roof in Germany, which is a hyperbolic parabola. Okay, thank you.
Questions? Questions?
Can you show me the statement of the main theorem?
Main theorem.
So is there, what happens if we restrict this family of convex sets, for example, for unipoles?
Okay, so that goes back to the if you impose further geometric constraints, a lot of nice things start happening. And for example, unit balls, you will have a weak epsilon theorem. If I'm not mistaken, you will have a strong epsilon theorem because unit balls are defined by semi-algebraic sets, and you will get bounded VC dimension, and all kinds of nice things will happen. So it's kind of not so interesting. It's
What do you use instead of unit balls, just translate that some complex value? Is it the same?
so translates a fixed convex set. Yes, it's the same because it will follow by some volume argument. So you need them to be general convex sets. So actually, Barani, who was the one who posed the conjecture, he believed this was true, and he proved it for the case of cylinders. So a planar convex set times a line. Okay, so infinite cylinders. And if you have pairwise, no, sorry. Oh, sorry, that was the other, my mistake. He showed that this is true with a linear function for pairwise intersecting cylinders. But his proof breaks down even if you have not cylinders, but kind of one-sided. So a cylinder is infinite in both directions. But if just a convex set times a ray, this proof doesn't work anymore. So going to infinity in one direction, then doesn't work anymore. And so, yeah. We don't know if there's a weak epsilon net for cylinders, but now that we have this counterexample, I don't think people are going to try to prove that. Yeah.
Other questions? Okay, let's thank the speaker.